All right, let's look at some of the chapter 4 stuff that you have to do. All right, so let's see. Why don't we look at, you have to expand and contract logarithms. Let's do one where you're expanding one. So let's say you have log base 3, and you have something like, let's do 27x to the second, y to the third, over z to the fourth. Okay. All right, so say we have one like that. So here we have all multiplication and division involved. Okay. So this would be one that would ask you to expand the logarithmic expression. Let me see how they worded on here. Expand the logarithm as much as possible. So what we would do is, if we have multiplication between things, then we know we can change it into the log. We can do the sum of the log base 3 of 27 plus log base 3 of x squared plus log base 3 of y to the third. And then because it's division, we would do minus log base 3 of z to the fourth. Okay. All right, then we have these, the x squared, the y to the third, and the z to the fourth that had you doing the log of a power. So you can bring those exponents down in front. So this would be 2 times the log base 3 of x. This term would be 3 times the log base 3 of y. And this one would be 4 times log base 3 of z. Those are expanded as much as possible. And then this one right here would be one where you could simplify that, because log base 3 of 27 is asking you for what the exponent on 3 would need to be to make 27 happen. So you just change that into exponential form, and you can look at it and see the exponent would need to be a 3. So this you could evaluate to get a 3. And then that's expanded as much as possible. Right? What if we had log base 2 and we had something like x squared plus 1 over y to the third? Okay? So on that one, this is a plus in here. There's no property of logarithms that says you could rewrite that as the log base 2 of x squared plus log base 2 of 1. So those are going to need to stay together. But then the quotient allows us to use that property of logarithms that says we could change it into the difference of these two logs. And then on this one, the 2 can't come down in front because that log base 2 is applied to x squared plus 1, and that's not being squared. So that first term is expanded as much as possible, but the second one I can bring the 3 down in front. So this would be log base 2 of x squared plus 1 minus 3 log base 2 of y. And I'd be done. Okay. All right, next one I wanted to do was to use the change of base formula to evaluate a logarithm. That's good when you're trying to do something like log, and it's a base that's not base 10 or base e. So most calculators don't have that. So let's say I wanted to know what the log base 3 of 300 would be. Okay. So the change of base formula says you could do log base 10 of 300 and divide that by log base 10 of 3. And then that would give you your answer. Let me grab a calculator real quick. You be working that one out. Okay. So I'm doing log of 3, log of 300. And I'm going to go ahead and just divide that by log of 3. Make sure you close the parenthesis after you type in the 300 before you hit division. And that turns out to be about 5.1 9 if I were to round to 2 decimal places. So that makes sense when you think about it, because doesn't this right here mean I want the exponent on 3 I would need to get 300? And so like 3 to the first would just be 3, 3 to the second would just be 9, to the third would be 27, the fourth would be 81. When I get to the fifth, 81 times 3, right, that's 243. So I'm getting close. 81 to I said 81 to the fifth would have been that. 81 to the sixth would have then been 729. So I know it's between 5 and 6. And so what we just found is that that would need to be about 5.19. So that's the change of base formula. Log of the inside, log of the inside divided by log of the base. All right, now there's 3 problems I'm going to do. One of them is solving an exponential equation. So that would be like, say you had something like 5. Let me get to that. There we go. Say you had something like 3 to the 7x minus 1 equals maybe 52. Okay. Well, this isn't 3 times 7x minus 1, so it's 3 raised to that. That x is an exponent, making it an exponential equation. So that's the type where what we're going to wind up doing is going in and logging both sides, log of both sides. Okay. All right, now at this point, I could bring this exponent down in front using one of the properties of logarithms, but it would be 7x minus 1 in parentheses, and then the log of 3 times the log of 3 equals the log of 52. Okay. Now, at this point, think about how log of 3 is really just some number. I could put it in my calculator and get a decimal. So it's just some number that's being multiplied by this expression that has an x in it. I'm working on trying to get the x by itself eventually, but let me get rid of those parentheses by distributing the log of 3. Okay, and then let's work on getting that x right here by itself. So let me add the log of 3 to both sides. When you do, you can't add the 52 and the 3 and get 55. That's not true. You'd have to evaluate the log of 52 and add it to what you get when you evaluate the log of 3. So here we would have 7x log of 3 equaling the log of 52 plus the log of 3. Okay? And then we're almost done. We need the x by itself, and there's multiplication between those things. So we can divide by 7 log of 3 on both sides. 7 times the log of 3 on both sides would knock the 7 and the log 3 out. And we wind up with x equaling that messy looking expression. All of that. Okay, so if you were needing an exact answer, that would be it. Now, one issue that can sometimes happen, especially on a multiple choice test, that would be full credit, is you might approach things slightly different. So like right from here, there's another correct thing that could be done. And so you might have gone in at this point and thought about dividing by the log of 3. Right? And then you'd have 7x minus 1 equals the log of 52 divided by the log of 3. Okay. And then at that point, you would want to work towards getting x by itself. So you'd add 1 to both sides. And then you'd have to divide by 7. And so you'd get a complex fraction in this case, because you'd have this fraction and then divided by 7. So that's not normally what you could leave as a final answer. So if you had done it that way, you'd need to be able to look at that and see that it was equivalent to this, okay? And how they could become equivalent would be if you cleaned up your complex fraction by multiplying by log of 3. If you did that and you multiplied the numerator by the log of 3, it would have to get distributed to both of these terms, right? So it would go to here and here. So it would knock out the log of 3 and leave you the log of 52 plus the log of 3 on top. But if you multiplied the numerator by log of 3, you'd also have to multiply the denominator by it. So those kinds of things can happen if you have like a correct, but a way of approaching it that leads to a different looking answer. You'd have to be able to see that they're really equivalent. Okay. All right. Solve a logarithmic equation. So that would be something like, say you have log base 5 of x minus 2 equals, say, 3 or something like that. Typically what you do on these is you use the idea of inverses. So you're going to do 5 to the left side and 5 raised to the right side, right? Because those are inverses, the left side would leave you with just x minus 2, and on the right you have 5 raised to the third power, which would be 125, okay? All right, now that same concept is what's going on if you think of it better. Like in your mind, you want to think of it as 5 is the base, 3 is the exponent, and so that would equal the x minus 2. Both ways lead you to the same final answer. So now all we got to do is add 2, and we wind up with x being 127. And that's what they want. You do need to check log equations to make sure what you think the answer is works here, in that it doesn't give you a negative number or 0. So watch the domain, okay? All right, and then let's look at one more. Here we go. Let's look at one where you've got to contract because you have more than one logarithm. So there was one that says solve the logarithmic equation using the properties of logarithms. So they're probably talking about one similar to one we had on our test that looked like this. Okay. Something like that, where you had more than one log here. So you needed to contract it into one logarithm. So log base 2. Because that's a plus, when we contract it, we're going to be multiplying those two. Okay. All right. So what we've got here is log base 2. And I'm going to go ahead and multiply out that inside part using FOIL. So it's x squared, and then it's negative 2x and a positive 4x, so that'd be plus 2x, and then 4 times negative 2 would be minus 8. All right, now at this point we need to do what we did on the previous problem. We need to work to undo the logarithm. So one way to do it is to do 2 raised to the left side, 2 raised to the right side, so that these are inverses, and you're left with x squared plus 2x minus 8. And that would equal 16 in this case. Or you can say to yourself, instead of doing that, you can say, so this is the base, the exponent would be 4, and that has to equal x squared plus 2x minus 8. You'd get the same thing, right? So let's finish solving this. Because it turned out to be a quadratic, when I go to solve it, I'm going to subtract 16 so that I get a 0 on that right-hand side. Because when you're solving a quadratic, unless you're using the square root method, you're going to need that. Then I'm going to give factoring a quick try. These normally will factor. So let's see, I'm trying to make 2 happen in the middle. So 1 and 24, 2 and 12, 3 and 8, 4 and 6. 4 and 6 would be the best bet. The 6 would need to be positive to make the middle term positive 2. And so now I can set each factor equal to 0 and get those two solutions. But don't be too quick to put those down as the answers, because with log problems, you need to make a mental note with log problems that you got to check your answers. Actually, go all the way to the beginning. So let's go back to the beginning right here. And the problem is if I put a -6 in, that's going to make me have to do the log of a negative number. And that, remember, gives you an error. So I'm going to rule this one out, not because this is negative, but because when I plug it in right here, I have a negative, and I can't do the log of a negative. So the only answer to this would be 4. And I am sure that one of the answers might be 4, another one might be both 4 and -6. And then there'll be some other wrong answers, maybe a -4 and a +6 or something like that. But anyway, so you'd have to know that that's not correct, that it's just +4 that would be the solution. Okay? So that's the chapter 4 material. Can't get it.